Okay, great. Thank you, and I want to thank the organizer for the kind invitation. Come to Rice. I'm going to treat this as a school as best I can and give hopefully a bit of a pedagogical introduction into how electron or quasiparticle interferometry works and how it can be used to interrogate a number of properties of strongly interacting topological systems and to expose ultimately, which I'll get to in the second lecture, anionic braiding statistics. So I'd like to give you a bit of background and to see what it takes to go from a theoretical concept to an experimental implementation, and what are the difficulties that the people working in the field have to address. So the concept of anyons goes back quite some way, actually to the late 70s, to the work of Linus and Marham. That was a mathematical discussion of what happens to statistics when you reduce the dimensionality from 3 to 2 dimensions. And they were the first to recognize that there were statistics other than bosonic and fermionic. But in the context I'm speaking about, in terms of the fractional quantum Hall effect, the field kind of got kick-started in the early 80s with the work of Frank Wilczek. And at the time, Frank was considering it seems somewhat contrived toy model, but actually turned out to be quite prescient. He was considering the quantum mechanics of charged particles tied to vortices. So if I have a composite object of charge connected to a vortex and consider the quantum mechanics of that, he realized that the angular momentum could be fractional as well for those particles, and by extension that the statistics would interpolate between bosonic and fermionic, essentially using the spin statistics, what we know from the spin statistics theorem. So the object, and this is where the definition of anion, the word, was a pun, right? It could have any statistics, it could be anything. So he considered the statistics of their object, of these composite objects, charge tied to vortices, which we now know in hindsight is the apt description of the fundamental objects of the fractional quantum Hall effect. And he said something that I think in hindsight's amusing and helpful. Although practical applications of these phenomena seem remote, I think they have considerable methodological interest and shed light on the fundamental spin statistics connection. Note the date, it's June 82. That was in late 81 and early 82 was when Stormer, Sui, and Gossert first announced the observation of quantization at 1/3. And there was a flurry of activity, theoretical activity trying to understand this, culminating, of course, in Laughlin's famous paper of the 1/3 state, the Laughlin wave function, and his model as the fractional quantum Hall effect as a quantum liquid with fractionally charged quasiparticles. Bert Halperin was also working trying to understand some of the other states that were popping up in experiments, specifically the hierarchical states. And what he found is, working through the generation of those, is that not only, as Laughlin had told us, were the excitations fractionally charged, but they had fractional statistics. And again, what I think is kind of a funny little comment. The appearance of fractional statistics in the present context is strongly reminiscent of the fractional statistics introduced by Wilczek to describe charged particles tied to magnetic flux tubes in 2 dimensions. Now this is 1982. It's before composite fermion theory and all that. We now know, 40 years later, that this is really the way to describe the fractional quantum Hall system. Shortly thereafter, Arovas, Schrieffer, and Wilczek gave a formulation of the fractional anionic statistics that would be familiar to modern graduate students of condensed matter physics in terms of taking the wave functions and basically calculating the Berry phase as you take one around another. And they put on, I guess, a firmer theoretical foundation that indeed, in addition to fractional charge, that the statistics are fractionalized for fractional quantum Hall quasiparticles. Okay, so the question is, in 1983, 84, Laughlin and the other theorists I've told you about have told us that the charge should be fractionalized. At 1/3, we should have 1/3 of the bare electron charge, and that the statistics should be fractionalized as well. And of course, you could say that the observation of the quantized plateau at 1/3 implies these conclusions, but the actual observation of both charge fractionalization and statistics fractionalization took a considerable amount of time. And that's the story I want to tell you about. How do experimentalists go from this theoretical construct to actually seeing it in the laboratory? So by now, the fractional quantum Hall effect is developed over many years in improvement in sample quality. I'm going to talk about gallium arsenide, but of course it's not just gallium arsenide. The graphene systems, oxide systems, there's lots of places where you can observe this kind of physics now. I just happen to be concentrating on gallium arsenide two-dimensional electron gases. So here's an overview of a typical sample these days down at, the density is about 1 × 10⁻11. It's at a fairly low electron temperature. And what you see really is just most of the time, the longitudinal resistance is near 0. It's interrupted by these resistance spikes when it goes between from incompressible to compressible states. And there's some insulating states in here. And of course, the Hall resistance, it has the classical linear background, but there are many, many plateaus associated with the various integer and fractional states. So, I chose this sample because it's low density. You can see a lot in a relatively low magnetic field. If you want to go in and study all the composite fermion states that can arise, you can do that by going to half or quarter filling, looking at all the states. If you're interested in investigating states that potentially are non-abelian, of course, the 5/2 fractional quantum Hall effect is a prime example. And here I'm just showing you, things have evolved. This is a very low field, 1.8 Tesla, full quantization. It's not exactly 0 field, but it's not so bad either. And so there's lots to see. And there was some discussion earlier of these potential non-abelian states. And so if I, just for fun, were to zoom in on what we can achieve now in bulk transport, here's 5/2, a large gap state. There's even 12/5, which may have even more exotic statistics if we can be not just simple Ising anyons, but Fibonacci's, if we could ever find a way to actually investigate it. And here's a zoom in on those states. So they're well formed. There's no ambiguity, at least through bulk transport measurements, about what's there. Now there is ambiguity about the topological order because the quantization of the Hall conductance tells us, of course, that we have this gap state, but it doesn't tell us that the particular topological order. And therefore, we have to work harder and do more experiments. So what I'm going to try to tell you about is, okay, so bulk transport experiments, just slapping some wires on and cooling it down, you can see all these states. But how do you devise experiments so that you can probe a particular property, be it charge or statistics, or hopefully both? And even here, the theorists were way ahead of us experimentalists. Back in the late 90s, Claudio Shimon, along with Kivelson, Sandy Wen, devised a scheme of doing the analog of Fabry-Perot interferometry now with quasiparticles. And you probably can't see it, I've underlined it. What they say, if you build this Fabry-Perot interferometer, you can measure, but I'll show it here. In this one paper, it's sort of amazing. You can measure the fractional charge. You can measure the fractional statistics. You can even probe the Luttinger liquid parameters of the chiral edge modes. So if you can build this, what they call a two-point contact interferometer, you can do everything. Now, of course, this is theory land, and they draw a cartoon of what it is, and here's their little picture, and oh yeah, you just put these things here and there. And so why that turned out to be harder than anticipated is really a story and where experimentalists come in, and we have to figure things out. And this is based not on just my work by any means. We came in relatively late into the field, but many groups contributed to this, and I'll try to mention them as we go along. Okay. I also want for students to think, I'm talking about anions in the fractional quantum Hall effect, and specifically in gallium arsenide. The reason is that's where our experimental tools are best developed right now, and where we can do really incisive experiments. And but that does not mean by any measure that anions can't be found in a wide range of systems. I'm very hopeful. It's a very exciting time in the field for this kind of work. You know, just a few examples of quantum spin liquids, and then topological superconductors, both the intrinsic and engineered types in hybrid systems. I also work on those where we try to use SOA superconductors to proximatize semiconductors with high spin orbit coupling. And there's been very recent work in graphene and the TMD stacks of observation of a fractional quantum anomalous Hall effect. This is just data over here. It's hard to see, but from the Jew group at MIT. And this is really cool. It's a really exciting time, and I'm expecting lots of things to happen in the next few years. Okay, but remember, those theoretical predictions are 40 years old. So what's the big deal? Why were we just dumb? Couldn't figure it out? And what I hope to tell you along the way over the course of the next two lectures is it's actually not so easy. And you have to design and grow the right materials. Then you have to fabricate fairly elaborate mesoscopic devices, and then you have to, measure them at very low temperature. And you got to get each part of this right in order to get at the physics you want. And where our contribution came in is really in this phase. I mean, once we got the devices, the measurements, we know how to do, but it took a lot of understanding by theorists trying to analyze previous generations of experiments in order for us to know what to do, what to fix. And I hope you'll get appreciation for that as we go along. Okay, so the sort of main point is that I'm studying the fractional quantum Hall effect. The excitations are anions, which means they'll have fractional charge and fractional statistics. They can be abelian, or they can be non-abelian. The case I'm going to focus on mostly here is for abelian statistics. Okay? And as I said, the bulk transport experiments are fairly straightforward, and you know what you have. But Laughlin told us in '83 that we should have fractional charge, but it took nearly 15 years and some very sophisticated developments in quantum shot noise measurements and samples and mesoscopic device design before the group at Weitzman, Moti Heiblum's group, and the group at SECT were able to measure quantum shot noise and see that at 1/3, yes, indeed, the charge is conveyed in units of E/3. Now, again, anionic braiding statistics, I'm going to talk about mostly Laughlin states today, or if at all. And here, the anionic phase is given by 2 pi times the effective charge. This was known by '84, the theorists told us, but I'm giving a talk now, and the first observation was in 2020, and so there must have been something challenging. So just to be clear what I mean, if we have localized quasiparticles, fractionally charged quasiparticles, represented by these spirals, okay, vortices, and I take one around the other, like so, that's equivalent to 2 exchanges. Normally you would think, well, you didn't do anything, you brought the system back to its original state, so there can't be any observable effect. In fact, for anions, there is a non-trivial phase develops, And for the 1/3 state, this anionic phase is 2 pi over 3. Okay, so Shimon et al. Told us that we should build Fabry-Perot interferometers, and what we're going to do is just that. But remember, this is an electronic analog of a Fabry-Perot interferometer. Unlike the optical system, where the photons don't interact, we have interacting electrons, and those Coulomb effects will play a role. But nevertheless, to get an idea of what's going on, consider the blue region to be the two-dimensional electron gas, and these yellow lines and T's are surface gates. They're gates we use to deplete locally the electronic charge in the 2-dig, okay? Now, we have source and drain contacts. Of course, there's lots of contacts around, but schematically, this is what we have. And this is all existing in a large perpendicular magnetic field. In the quantum Hall regime, current is carried by the chiral edge modes. So a chiral mode comes into this first region between the two gates. That's called a quantum point contact. It's a narrow constriction. And we use the voltage to partially backscatter some of the current in a controllable way from the lower edge to the top returning edge, going back to the source contact. Most of the current goes on into the interior of the interferometer. We have a second QPC where we again partially backscatter the current that's coming through the interferometer. Now, this is the interference loop. This dashed line, the quasiparticles or electrons along this path recombine with the charge carriers that were scattered at the first QPC, and this is a coherent process. We're in a coherent regime, so they interfere. We build up interference depending on the relative phase that is built up inside the interferometer. And what we actually end up measuring is what current comes out at the drain, okay? So the surface gates define the electronic interference path. They tell us where the electrons or quasiparticles must go, and the QPCs act as our electronic analog of a beam splitter. We use those to partially backscatter some of the current. They partition the edge state, and that's what gives rise to the interference. Now again, this was theoretically worked out in a seminal paper of Shimon et al., but over time, a lot more detailed theory needed to be developed, and a really good reference for this is Bert Halpern's paper, Adi Stern and others, from 2011. And I'll draw on that a lot. So if we consider the current that flows through the system, we give an excitation to the source, we measure the current that comes out of the drain, the current is going to be proportional to the transmission coefficient of these QPCs, the amplitude of the transmission coefficient squared for QPC1. Of course, there's also an equivalent term for QPC2. That's sort of boring. But there's this interference term or cross term where we have this cosine theta sinusoidal dependence. Now that theta is not the anionic phase, it's the interference phase, the thing you actually see in the measurement. But if let's just start out with the easiest case where we're dealing with just electrons, say we're in the nu equals 1 or nu equals 2 integer quantum Hall effect. Then this interference phase is nothing but the Aronoff-Bohm phase. A here is the area of the interferometer. B is the magnetic field perpendicular to the interferometer. Of course, that's the flux through the system. And the AB phase, the interference phase, will be periodic in the fundamental flux quantum, H over E. So if we change the area or we change magnetic field, we should see periodic oscillation. So we can measure interference by measuring the electrical conductance of this device. We can operate the device in two ways. We can change the area by changing the voltage on these two plunger gates, they're called. You see these two T gates. Think of it as an accordion. We can, by putting more negative voltage on, we can make the interference area smaller. By releasing or making more positive that gate voltage, we can make the area bigger. So we can squeeze and expand. Or we can change the magnetic flux by changing the magnetic field. So there's two ways to operate this device. Now, if you plot conductance as a function of flux or magnetic field on the x-axis, and the gate voltage, the plunger voltage on the y-axis, you can make 2D color plots of the conductance. And theoretically, what you should see if we're interfering electrons in the integer quantum Hall effect is a series of lines of constant phase. Constant phase means constant conduction that have negative slope in the B versus delta flux versus delta V plane. This barbershop pole-like behavior is what you expect if the evolution follows this simple description I've told you of AB development, okay? And now, what we're going to find out is it's not so easy, but just keep this picture in mind because this is what we're trying to get, at least in the integer effect. Now you can ask, okay, what happens when you move to the fractional regime where you have anions with fractional statistics and fractional charge? This interference phase gets modified in two important ways. The AB term is now scaled by the effective charge of the quasiparticles. The periodicity changes, okay? So that is a means of measuring effective charge, the change in periodicity. It is also directly depends on the number of localized quasiparticles, those little spirals that are localized in the interior of the quantum Hall droplet, and the statistical phase. So you can imagine I can only add or remove quasiparticles discretely in units of 1, 2, 3. So if that happens, my interference phase will slip. There'll be a phase slip. It'll perhaps look like noise or a glitch. But if I add a quasiparticle or remove one, that can only be done in a discontinuous fashion. So there'll be a discrete change in the interference pattern. So you can imagine looking for jumps, not only a change in the periodicity from the integer regime, but for discrete jumps as well. Okay? And like I said, this has been known for quite some time. So what's the problem? And what did we have to figure out as experimentalists? The field had to figure out. Okay? Well, the problem is this interferometer is an interferometer of strongly interacting particles. Electrons, quasiparticles, are subject to the Coulomb force. So while our naive expectation for AB interference has these lines of constant phase with negative slope in the delta B, delta V plane, when you do experiments, and many experiments, but I'm just showing you some data from an early experiment of ours, you see the barbershop poles, but they're pointing the wrong way. The slope is completely wrong, okay? And this was a mystery and took a lot of experimental development, but also a lot of theoretical work. And what it turns out is that the bulk edge interaction causes the area to change. So remember, I'm supposed to have an incompressible liquid or fractional regime or an insulator in the interior of the interferometer. There's no low-lying excitations. But along the edge, the perimeter, I have the chiral edge modes, which are gapless, okay? And if I change the charge in the interior of the device, the edge modes, depending on how strongly they're coupled to that, can respond to the Coulomb effect. And if the coupling is too strong, then what happens is, say you increase the magnetic field, you think you're increasing the flux. What happens is the electrostatic energy is minimized by shrinking the area. So you cannot change in the limit where you have strong bulk edge coupling. You cannot change the area and be independently. The flux decreases even though you increase the magnetic field. Okay, so counterintuitive, but that's the price we pay for working with a mesoscopic device. I'll tell you about the length scales. Now, you could say, okay, why do you care? Well, in principle, this makes braiding unobservable because if the Coulomb interaction is too strong, every time a quasiparticle is introduced, there'll be a compensating change in the area so that the phase slip is actually 2 pi, unmeasurable. And so this is a serious problem. It makes braiding unobservable. And so this is a challenge that the field had to overcome. So I just want to keep that in mind, that this strong bulk edge coupling is a limiting factor, or can be, in measuring interference of anionic quasiparticles. Okay. As it turns out, there's been lots of theory work in this area. I'm just putting a few citations down here. But this is from the Halpern paper. Depending on these coupling parameters, the coupling parameters of your real device, you can go I'm talking just about the integer states now, all the way from the pure AB limit, where the bulk edge coupling is minimal, the barbershop hole. There can be intermediate regions where you get checkerboard patterns in the interference, where there's some bulk edge coupling, but there's still some component of AB. And depending on how you tweak the parameters, if you go all the way to the Coulomb-dominated regime, you get this lines of positive slope, okay? And so if you're not familiar with these types of devices, what I really want the take-home message to be is that the regime of operation depends on the ratio of some parameters. I'm calling them here KIL and KI. They're effective parameters that determine the electrostatic energy of my interferometer. The KIL parameterizes the strength of the bulk edge coupling. If I change the charge in the interior, how does the edge respond? While KI is the edge stiffness. Remember, it costs a finite amount of energy to add charge to the edge, going at a certain velocity. And so depending on the ratio of these parameters, which I hope to show you, if not today, tomorrow, can be measured in situ in the device, you'll get a range of behavior. And we have to move towards the left-hand side, from my perspective, the left-hand side of the plot in order to be sensitive to the anionic phase. If I'm over here, I miss it, okay? So how did we make progress? How did the field make progress? Well, there was lots of experiments along the way, and one that I would like to show you as an exemplar, I think, that demonstrates how we built on earlier findings is the work of Charlie Marcus when he was still back at Harvard in 2009. Charlie built interferometers, and what he did is, in this experiment, something that was very helpful to us, insightful. He built them of different sizes. At the time, a small interferometer was 2 microns squared, and he put a top gate on top over the entire area. So there's a metal plane a couple hundred nanometers away from the 2-dig, and this is a relatively small device. But he also built a humongous one. If you're thinking of a quantum dot, he built an interferometer with 18 micron squared area. That's really huge. Again, he had the top gate. And what he found is in the small device, he always got Coulomb-dominated behavior. He couldn't get away from it. It was always in this strongly coupled regime. So that's not good. What he did see that was interesting, though, when he looked at this very large device, where I made it larger, so I suppressed the Coulomb charging energy. If you think of it, a quantum dot is, what is the charging energy of a quantum dot? It is reduced as I make the device bigger, and I have this big metallic plane on top. He was actually able to see AB-like oscillations here. I mean, you can see that they have the right slope. The colors aren't the same as I use, but the behavior is the same. But the problem here is if you look at the field scale, this is down at half a Tesla. And if I consider the filling factor, that's the ratio of the density of electrons to the flux quanta penetrating the system, that, I want to be at 1 or lower. This is extremely high filling. It's like nu equals 22 or something like that. So far away from the regime we want to operate. The problem here is, although we got AB, because it had a long path length and other details of the edge confinement, the coherence was poor. And as you turned up the magnetic field, the effect just went away. So by the time he got to a field that would put the device in an interesting regime, there was no more interference. Okay? But this was a valuable lesson. It says if you make the device bigger, you reduce this Coulomb energy scale, long-range Coulomb energy scale, not short-range. You can get more towards the AB regime. But you can't keep this very large device or you'll never see coherent transport. So the problems are these Coulomb effects I've been talking about, but also the sharpness of the confining potential at the edge. You want to make the confining potential, how the potential changes from the bulk to the edge of the sample as steep as possible, because that gives you the largest edge mode velocity, and that aids in coherence. So if you make small interferometers, you get good coherence, you have a short path length, but they're Coulomb-dominated transport. You get this type of behavior. If you make large interferometers, you get AB oscillations, you reduce the charging energy, but the coherence is low because you have a long path and you haven't done anything to boost up the edge velocity, okay? So the innovation that my group made was, well, Charlie was onto something good, and it wasn't just him, there was the Weissman group as well, there was others. He made the thing big, and he put this gate, but he didn't, that was ex situ lithography, and that sets the distance between the metal gate and the 2DEG, it's very far. We have this MBE system, so what we thought about doing is actually building the 2DEG that we're interested in probing inside a parallel plate capacitor. We'll do it through growth. So we have a primary quantum well, this blue region that's 30 nanometers. That's where my primary two-dimensional electron gas resides. But what we did is we said, on 25 nanometers away on either side, we put additional quantum wells, and we populated those with electrons. In fact, we populated them with much more electrons than in the primary well. So what we're doing with this is we have this middle 2DEG that we want to build an interferometer out of, but we're placing it in close proximity to these two metal plates, and they quench the Coulomb charging energy and allow us to get into the right regime. We can do that because we have the MBE. Now, you have a complicated system in that you have 3 two-dimensional electron gases separated by, 25 nanometers. And in fact, the ones in the ancillary quantum wells are much higher density than the primary quantum well. This is going to make your device implementation more complicated, but it's a small price to pay because by going to this heterostructure design, we're able to really get in the right regime for measuring anionic statistics. And I'm going to try to build that up for you in the time we have. So if you look in the middle panel, so here's the ancillary quantum well below the prime quantum well. Here's this, what we call a screening well. Here's the second ancillary quantum well above it. And so it's like Charlie's experiment, only I went in and put a gate on the top and the bottom, I put them really close. Okay. And even with this and processing the device, all the stuff I'm going to show you about how you have to make the device, the quality of the transport is remarkably preserved. Okay. Now I'm going to have to go to this fairly advanced device platform, but again, it's worth the effort. Okay. So what I'm going to have are 3 quantum wells, and they're all going to be shorted through the ohmic contacts. There's no way to separately contact these with this sort of separation. So, if I'm going to measure transport and I just measure the bulk transport, it'll look like a mess. But what I can do is build a series of gates, shown here on the left in this cartoon, looks like a subway system, above and below that I can use to turn on and off the screening wells locally where I want them to, so that I can control conduction. So I need to eliminate parallel conduction through the screening wells. And in this, what we did is we borrowed a technique Jim Eisenstein used a long time ago to study correlated bilayers. It was completely different physics and they weren't mesoscopic devices, but we just wholesale stole his technique, okay? So we put, around the omics, we put a gate on top, and by biasing it, we can cut off the connection to the top screening well, and we can gate from below and cut off the connection to the lower screening well so that the ohmic only sees the middle quantum well. Now, these gates are out at the periphery of the device. This is a big mesa. Our mesoscopic interferometer, the tiny little thing, is way in here. So it still sees the full charge density of the upper and lower well. It's there to screen, but it doesn't impact our transport. And I'll try to convince you of that now. Now, in order to do this, this is also a part, I think, it's good to appreciate for students, what it takes to get there. So it's like, okay, how are you going to do this? Well, you have to start out with a bare MBE wafer that's been properly designed and grown. You have to etch it out. You put some ohmic contacts on it. Then you have to pattern the top surface gates that define the interferometer and evaporate those. Okay, those are fine gates. And then you have to pattern and evaporate the fan out to the bond pads and the top ohmic gates. So there's an additional layer of gates that go on. Okay, now we still have a problem. We have this bottom screening well, but it's 1.5 miles away from any gate on the backside because it's sitting on a half millimeter thick gallium arsenide substrate. So what we do is we mount the wafer to a carrier chip, flip it upside down, polish it back so that we get down to 50 microns on the backside. Okay. Then we do backside lithography where we come in and put gates, align gates on the underneath side. It's been flipped over, and we connect up to these. Oops, I didn't come on the right color. Connect up to these backside gates. Now the sample is pretty fragile. It would break if you tried to hold it right now. So we have to mount it. So we mount it on basically the chip carrier right away. Now that it's has mechanical stability, we can dismount the carrier chip and the glue we used, take that away, and then bond up the device and apply gate voltages to cut off the top screening well, cut off the bottom screening well, and then define the interferometer, and this is what you get. But, getting to this final device takes a lot of iterations and process development, and it's important to keep in mind what the thing really is at the end that you're using for measurement. Now, what it looks like in the end of the day on a PCB board is this thing. Looks like a mess, right? But that's all lithography layers. And then that sits at the bottom of a dilution refrigerator, which we use to cool it down to approximately 10 to 15 millikelvin. And if the experiment works and everything's great, then you can have your art department make fancy looking graphics that look really cool and all that. But remember, in reality, it's this messy thing that you have to fabricate. Okay. So let's get to the business of measuring it and how, I'm kind of a stickler for control experiments where if you're going to make a big claim about something, you have to understand the device pretty well and make sure you know how it's operating and you can control its parameters. So if we first just measure the conduction through this, say the Hall resistance and the longitudinal resistance, I'll show you Hall, through this device without taking care to separate the different layers, what you see is the Hall trace looks like that. It looks like a mess, right? A very high density. And maybe there's plateaus, but there's different layers with different concentrations, so they're not lining up. If we gate away one of the screening wells, do you see the change in the Hall conductance? It actually shows, reflects that we're sampling a lower smaller density because we only have one, we're only shorted by one screening well. If I do both of them, I can measure the Hall resistance through the device and I get the proper density and you see all the states develop. So this tells us that this is a first check that the pattern gates are working properly and I can actually look at the transport just through the primary quantum well. Now I said early on that I need to quench this charging energy of the mesoscopic interferometer in order to get into the right regime for AB and seeing anionic statistics. Well, how do I know I did that? Well, one way is this interferometer, I call it an interferometer, but if I were doing another experiment, I could just call it quantum dot. And the quantum dot, I know how to do Coulomb blockade spectroscopy on. We can pinch down the QPCs where it's zero magnetic field. We can make it so it's an isolated island. We have to tunnel on and off. And if you're familiar at all with quantum dot physics, you may be familiar with this Coulomb diamond plot. We're looking at non-linear response. We're putting a finite bias across the system. And then we, as a function of the plunger voltage, look at the conductance, okay? Now, this Coulomb in the black regions, the dark regions is where there's no available state, so we don't get conduction through the device. And of course, the other colors are where we bias the system so that I can actually have a resonance that I can go through and see conduction. And these Coulomb diamonds, the height of these black regions tells us about that charge area, how much energy it takes to put charge onto the little dot. And remember I showed you that plot of my own data of Coulomb diamonds, of the interference in the Coulomb dominated regime where the slope was going the wrong way. If I measure the charging energy of this, I get about, that particular one, about 200 micro EV. Tells us the energy scale for putting charge on and off. Now, if I repeat the same thing, but now use this screening well heterostructure, as I've been describing, exact same geometry, everything is the same, and I measure the Coulomb diamonds, it's even hard to see the Coulomb diamonds. The charging energy has been greatly suppressed by, excuse me, approximately a factor of 10. So we can characterize these energy scales in situ by looking at the Coulomb diamonds. That tells us what our self-capacitance is, and the screening wells that we've added dramatically reduce this charging energy. We went from 200 micro EV to 17 micro EV, and that is going to get us into the AB regime. Okay? Now, we can look at this charging energy versus interferometer size and with and without the screening wells. And if we, this is a plot of that charging energy measured in the manner I just told you. These are data points, and where we just scale the area. And you can see the data from the screening well samples is consistently below the data without the screening wells, okay? And so there's just, you know, it has a dramatic impact, and we can see it in the experiments. All right. There's a second benefit that I'll allude to more tomorrow probably, but these screening wells also sharpen the edge confinement. Remember, we're talking about edge modes that circulate around the perimeter of the interferometer, and their velocity is set by the gradient of the electric field at or the gradient in the potential, which gives the electric field as you transition from the bulk to the edge. And the screening wells help in that way. It's like shining a light through a mask. And so it projects down straight onto the 2-dig and makes the, rather than healing over a longer distance, makes the edge confinement much sharper. So if I look at a single QPC conductance, say this is at nu equals 1, I have one full unit of quantized conductance transmission. I squeeze the accordion box in, and then rapid loss of conduction down to 0. Okay, that's what you want. It tells you it's sharp. Here's a calculation of the differences with or without the screening wells in. But just for comparison, here's some data from the literature where they were also at nu equals 1 using non-screening well structures, standard gallium arsenide structures, and making the same plot. And you can see as a function of gate voltage how it goes from 1 unit of conductance. There's lots of resonances. There's even an intermediate plateau-like feature at 1/3 before the conductance drops off. And that's something that's associated with a phenomenon called edge reconstruction in the fractional Coulomb Hall regime. Graphene is really good because I think it will have very sharp edges because everything is pretty close by. The graphite gates are really close, just like in my case. But this is a known problem in gallium arsenide and can really influence your interferometer results. So, but by going to the screening well, we have very sharp confining potentials. Okay? We can measure the edge velocity, or the edge velocity is going to determine the coherence. And so there's ways of measuring in situ by, again, doing differential conductance measurements where we apply a finite bias across the interferometer, and we build up as a function of source drain bias now. This is actually we're moving away from the zero source drain bias limit of conductance. Now we're measuring it as a function of finite bias, And these nodes develop. If you want the details, you can see it here. By applying a finite bias, you're adding momentum to the edge state, and you can find this double periodicity. And so the delta, there'll be nodes in the conductance, and this is the standard stuff I've already shown you, but it's proportional to the source drain bias, the length, those are things we already know, from which, where the position of the nodes are, we can extract the edge velocity. And we can do that in multiple regimes by looking at where the conductance goes to 0. So in this case, we have one edge mode at nu equals 1. These zeros tell us about the velocity. We can also do it at nu equals 3, where we have 3 edge modes and independently scatter them. So this is something that, by the time we get to the interference experiment, we already know a great deal about how our device is performing, and we can extract parameters independently. Okay? So I'm gonna, how much time, what time does it go to? Yeah, okay, it's about right. So now let's, see where the rubber meets the road and build an interferometer. So this is what our actual interferometer looks like. Now, here's a scale bar of 500 nanometers. It's much smaller. This is the biggest one we ever made. It was 1.25 microns by 1.25 microns. Okay, much smaller than the ones I showed you earlier. Nevertheless, we take this guy and go up to 4.5 Tesla, which is nu equals 1, and we see lines of constant phase with negative slope. We can extract the periodicities here that give us the effective area of our interferometer. That's the electronic area. And by looking at the field periodicity and the gate voltage periodicity. And what we see here is that we have AB interference in a device that's 20 times, now it's just the integer, there's no anyons yet, but it's just building up confidence that we know the device is working properly. There's AB interference in a device that's 20 times smaller than had previously been achieved. Why do I care? Because that helps with coherence. The interference is large amplitude, it's easy to see, and it survives up to hundreds of millikelvin. It has really good coherence. I'll show you that now. If we measure the interference pattern as a function of temperature going from the base at this particular experiment was 13, but we went to 100 and 200 millikelvin. There is a dampening, a loss. I mean, you still see it, it's pretty clear that you can still see, even in the black trace, the sinusoidal dependence, but the amplitude is reduced. So we can look at this as a measure of coherence. So at lowest temperature, largest amplitude, and if we plot the changing conductance in such a way, here we've just defined this quantity, what is that letter? I forget the name, but that guy right there is the coherency factor, and as a function of temperature, we just plot it going from lowest temperature up to highest temperature. We can extract an effective energy scale. And at least for nu equals 1, in the integer effect, that temperature scale is 200 millikelvin, which is really good because it's much higher than our electron temperature. So we know we're in a coherent regime. Okay? Now I take that same sample. This is the first experiment. I go from nu equals 1, but I just crank up the magnetic field. In this first experiment, that would place 1/3 around 13 Tesla. Okay. So same device, all I do is crank up the magnetic field, and again, we see lines of constant phase with negative slope. This is AB-like oscillations in the fractional regime. And this is work from 2019, and this was the first observation of AB oscillations in the fractional regime. Previously, the experiments have been limited to lower magnetic field in the integer regime, largely because of this coherence effect. But we are able to go up here, and in the same device, by looking at the ratio of the periodicities in field and gate voltage, how they change, we're actually able to extract the effective charge And by just looking at the change in periodicity and knowing lever arms, basically how the area changes as a function of gate voltage, you can extract the effective charge, and we get 0.3. Now, that's not so exciting, because it's 2019, and it had been measured in the late 90s by quantum shot noise. But this is the first step along the way to getting into a regime where we could also look at anionic statistics, and that will be the focus of tomorrow's talk. So if I were to summarize the experimental results so far, the story I've been trying to tell you, build up, tomorrow will focus really on the results at multiple fractional fillings. To examine interference in a fractional regime, we must engineer devices that suppress this bulk edge coupling and promote fast edge velocity. And that's why it took the field, not just me, it took a long time, because we had to learn how important that was. Our contribution is the screening well header structure with top and bottom gating accomplishes this task. And so far what I've shown you is strong and highly coherent AB interference in the integer and fractional regimes. Now that's not showing you anionic statistics yet, it's showing you that they're fractionally charged quasiparticles. And tomorrow we'll focus on the fractional statistics. But this is the machinery we had to build up in order to get to that point. Thank you.
Any questions? Really stand by the voltage coupling will result in a decrease of error, will increase in magnetic field.
Yeah, and I can show you that more tomorrow. You can write an expression for the overall electrostatic energy of the system. Okay, and it turns out you can just see what minimizes, and there's a term that has to do with the energy to add particles to the edge, particles to the insulating bulk, charged particles to the insulating bulk, and then the cross term. And if you, depending on the ratio of the parameters, what you'll see is you minimize that electrostatic energy by shrinking the area. It actually spits out charge and therefore reduces the overall electrostatic energy. I definitely will show you the equations tomorrow, how that comes about. But, you know, you can imagine if you just suddenly change the charge distribution or density in a region, and you have a test charge that's circulating around the edge, that's not too far, the edge has to decide, what do I do in order to minimize the electrostatic energy? And it turns out that in a certain range of parameters, it's better to reduce the overall size of the of the dot.
So I'm wondering why this diffusion region is the screening well. Why does it have to be so large? Is it like in the bigger you show? The diffusion region is
Are you saying depletion?
yeah, the diffusion region in the screening well. We had a red.
It's not really large. It's way far away. Well, I don't know what large means when it's so far away, but maybe something wasn't clear in my presentation. If I go back. Yeah. No, that's defining, this is just a schematic. So the depletion, this is about the interferometer. Yeah, this is 20, yeah. So let me show you the device or the picture. The gates that deplete, you see this one that's out on the arm? So this is the blue thing is the mesa. The interferometer is a little guy in there. What I'm actually depleting is these guys out here, and the guy who runs underneath, so that there's no galvanic connection out to these ohmic contacts. But the screening well TUDEGs are still fully populated in the business area, the region that matters in the center. It's not depleted there. It's only on the periphery so that I can selectively push and draw current out through only the primary quantum well.
Any other questions? I do have one naive question. So when you design for the large 50 translators, there's a lot of parameters that you can
Sure, sure.
and then you show this electrostatic calculation. So could you explain a little bit what?
Yeah, okay. So you could think of it in terms of design constraints. One design constraint is I can't put those screening wells within a magnetic length or two, because then I will screw up the short range part of the Coulomb potential, and that will affect the fractional quantum Hall state. So I do have a hard limit. You know, if I calculate what the magnetic length would be at whatever state I'm trying to look at, I have a hard wall that I have to be at least a couple magnetic lengths away so that I only screen the long range part of the Coulomb potential and don't mess with the short range part. So that's one hard limit. Then the other design rule is I want to have higher density in the screening wells and not be symmetric. So I don't want those quantum wells going into an insulating quantum Hall state at the same time the guy I'm interested in goes insulating, right? Because then they're not going to screen. So what I have to do is make them asymmetric, hopefully higher density, because you know it's not a perfect metal at 10 Tesla. And I have to make sure that the state that I'm interested in exploring, when I get to that magnetic field, those guys still have some compressibility. They don't, you know, imagine if they were all the same density. They'd all lock in. And that would be a mess, because then you wouldn't have screening. So I don't know if we have very, but we do have like a set of rules that we have to follow in order to make the thing work. And then we play around and, you know, are perturbing around those constraints. So, you know, I'll give you an example. We are now trying to design devices to do interference at 5/2. And it's a challenge. It's a super challenge because a couple of things are working against you. The magnetic length, well, the quasiparticle size has many magnetic lengths at 5/2, and since 5/2 is typically at lower magnetic fields, the magnetic length itself is already pretty long. And so, and you also have to be, you have multiple edge modes at 5/2, like you do at 2/5, which I'll show you tomorrow. And so if you have to interfere inner edge modes, they're typically moving slower. They're in the less steep part of the confining potential. So maintaining coherence is harder when you have to interfere inner edge modes because they're slower. So there's a lot of like heuristics that we have to use in order to figure out what device, and then we try a bunch. But they're controlled. I don't mean try a bunch like it's random. We perturb the parameters and the growth. We make the device see how it performs, and then feed back on it.
Any other questions? If not, let's thank the speaker again.
Good.